And now in our discussion of series, we're going to look at some applications. So first thing, repeating decimals. Okay, and also looking at rational numbers. So when we encounter this, you may have seen this before, maybe not. We can take any number, any number that has repeating digits, and break it into its repeating part and non-repeating part. And so in this example it says express the number below as a ratio of integers. So if I break this into its repeating part and non-repeating part, so its non-repeating part, I'm going to say this is 6.2. That's the non-repeating part. The repeating part, if I look at it, it'd be 0.054 would be the first kind of chunk that repeats, and then the next chunk that repeats would be, let's see, so 0.054. And then plus 0, 1, 2, 3, 4, 5, and then 5, 4. Okay, and then so on and so forth, right? So the 5, 4 would just continually move down in my list. Okay, so what I can do is I can think of, well, this whole thing here, 6.2 is going to stay the same, but this repeating part is really a series. I can say this is the series from n is equal to 1 to infinity, and then I would say this is 0.054, okay, or also known as 54 over 1,000 times, and then it would repeat every 2 digits thereafter, so it'd be times 1 over 100 to the power of n minus 1. Oh, and then that's a geometric series. Okay, I know how to find that. So I could also say 6.2 is 62 over 10, and then this is plus. And if I find the sum of that, right, then this is going to be the first term, 54 over 1,000, all over 1 minus 1 over 100, right, by infinite geometric series. And then a little bit down the road, I'm just going to skip the arithmetic. You can verify it on your own. I ended up getting, once you simplify, 344 over 55. Again, I encourage you to pause the video and work out the details just to confirm all that, but that's what I got. So the idea with the repeating decimals or rational numbers, express it first as its non-repeating and then repeating parts, and then represent the repeating part as a series. Okay. Another example, and we'll see this next example pop up all over the time. When we look at series, we're going to talk about this idea of radius of convergence, and so there's going to be a variable x in here as well, along with n, which is kind of our step indicating the position in the sequence that we're at. Okay, our goal is to figure out what values of x cause this series to converge or diverge, or really diverge. And so what we want to do is look at making these things into geometric series as much as possible. Okay, so we want to figure out the values of x for which the series converges, and then find the sum if we can. So if we find the values which make the series converge, okay, well, this looks a lot to me like n is equal to 1 to infinity, and then this is going to be, I can write this as x plus 3 over 2, oops, erase, 2 to the power of n, and well, doesn't that look a lot like, a r to the n, right? So then in this case I could say, oh, well, a is 1, right? And then for convergence, we knew that this thing converged if r in absolute values was less than 1, right? So then let's just make that x plus 3 over 2 less than 1 for convergence. Oh, and then that's an absolute value inequality. Okay, I can write that out. Negative 1 less than x plus 3 over 2 less than 1. Okay, solve for x. Okay, multiply by 2, subtract 3, and I'd get negative 5 is less than x is less than negative 1. Okay, so this is what I would call my radius of convergence. So this is the values for x for which the series converges. So that's the first part. Okay, now for the second part, that again we would need to figure out the sum. Well, the sum of the first term, okay, formally it's n minus 1, right? So we need to take out n minus 1, so I'm just going to say the sum here. To find the sum, I would take the first term, so pull off the first term here, x plus 3 over 2, and then divide that by 1 minus x plus 3 all over 2. And again, I'm going to skip the algebra. At the end of the day, what I got was x plus 3 over negative 1 minus x. Okay, and again for x in that certain range. Okay, so assuming that x is in this range, then we can say that it has a sum, and then we would have the particular value of x. Okay, so that's an example where we have to find the radius of convergence by comparing it to a geometric series, and then figuring out the range of values from that geometric series comparison, and then once we have that, we can find its sum. Okay. Now, the rest of the examples that you'll see in the slides here are very, very good. Okay. I'm going to set up a couple of them, and then the rest I'm going to say, if you're interested, look at my annotated slides through the Google Drive folder. Okay, so we can talk about Cantor sets, and both the Cantor set and the Sierpinski carpet. That one is actually in your homework, so I'm not going to do that one. But these are examples of fractals, and I absolutely love fractals. But the idea with the Cantor set is that if you have a line, okay, call it a line of length 1, so it goes from 0 to 1. Okay, and this would be kind of the 0th stage. And then in the first stage, you take that line, divide it into 3 sections, and remove the middle third. So I take that part out. Okay, so this is 1/3 and 2/3. And then the second stage, you repeat that process, but again, take out the middle third. Boom, boom. So 1, this is 2/3, this is 1/3, and then this is 0, and then this is 1/9 and 2/9, and then this would be 5/9. You know, because that's that's 7/9 and 8/9. Okay, and then again, third stage, you divide each of the remaining segments in thirds, and then take that out. Okay, but if we think of Li, so if we define the sequence Li as the length of the removed segment on step I, okay, then L1 is going to be 1/3, L2 is 2/9, L3 would be 4/27, L4 would be 8/81. Okay, so you start to notice a pattern here. So then if I'm curious about the total removed length, that would be the sum from I is equal to 1 to infinity of Li, right? And so this, I could think of this as 1/3, right? Let me write that over. The series I is equal to 1 to infinity. And then the first term, which is 1/3, times the common ratio, which appears to be 2/3 to the I minus 1. And then that's a geometric series, right? Which I can find its sum by saying it's 1/3 over 1 minus 2/3, which ends up being 1, which is super interesting as a mathematician, because we're removing essentially the whole line, right? So even though we have this process where conceptually we should have something left because we're always dividing into 3, taking out the middle, right? We end up removing the whole line? Question mark? Okay. Something interesting also happens with the Sierpinski carpet, which you'll see in your homework. So I'm not going to do any more with the Sierpinski carpet. Again, if you want to look through my annotated slides, you're welcome to. And for this last question here, with the circles and the triangle, very, very interesting question to work out. The mathematics, you have to use a lot of geometry. Again, this is like an extreme challenge problem, so I want you to try to do this. And you'll find that the formula, it works out quite well, but it makes you use a lot of tools, so it's kind of fun to do as a review. And that is going to wrap up the videos for this week. So you can look for a lot of geometric series, telescoping series, convergence, divergence in relation to series, and also remember that test for divergence, super important when we're thinking about whether the series exists and converge or not.